Hi, welcome to another video on uh, basics of electronics. So in this video we will look at parameters of Opamp and some properties of feedback systems. Of course, we should be knowing some basic concepts of electrical circuits, that is Ohm's law, KVL, KCL, and of course we should be knowing some basics of amplifiers. So these are the some minimum things so that you can able to get the best out of this video. Let us move on to uh, we know that so op-amp is nothing but an amplifier. Op-amp is nothing but an amplifier, meaning this op-amp symbol what we have, this is inverting terminal, so there is a non-inverting terminal, and this is we labeled as V minus, V plus, and this is V naught. Of course we're going to have the supply voltage plus VCC minus VCC. And we also know in general how does an amplifier can be represented, so in a block diagram fashion. So this is how an amplifier can be represented, something like this. This is, so we have this as A naught times of V in, and this is R out, output resistance. This is R in, this is plus or minus V in, this is plus or minus V naught. This is how an amplifier is represented. This is the typical op-amp. So let us try to find out op-amp parameters. So now let us take the parameter here. This is the parameter we are looking at, and what is its ideal value, and what is its typical value that you're going to have, which will be in real time, value. So now if you consider what is the voltage gain of an amplifier, voltage gain of an operation amplifier, so ideally this gain should be infinite. So this is ideally infinite, whereas this typical gain can vary from 10 power 4 to 10 power 8. So this is the range of typical gain of the op-amp. This is voltage gain. When we say gain, it is invariably the voltage gain. Then comes what is the input impedance. So as we already discussed in the previous videos, so any amplifier should have infinite impedance, so that when you have a source with some source resistance, the entire voltage, that is Vs here, with this R signal, and if this V in has to be Vs, so then R in should be infinite. So input impedance has to be infinite in an ideal case. In case of typically, this is few hundreds of, maybe from few mega ohms to few hundreds of kilo ohms. So this is the range, so this should be large. And then comes the output impedance. So output impedance, we know that whatever gain we have, gain times the input voltage is the voltage that you have. If this entire voltage has to reach to this output point, then this R out should be 0. So this should be 0 typically, 0 ideally. Typically it is few tens of ohms to hundreds of ohms. This you can see, this is still in ohms, tens of ohms, hundreds of ohms. It can be even 200, 300 ohms. So this is the range. It is in terms of hundreds of ohms. So ideally it should be 0. Then comes the bandwidth. So bandwidth is nothing but it is the range of frequency over which this amplifier will amplify the signal with the same quantity. So ideally the bandwidth should be infinite. This is actually in, this is a ratio, whereas this is in ohm, this is in ohm, this is in hertz, this is in hertz. So this should be infinite hertz, but typically this will be in terms of hundreds of kilohertz to few few megahertz. So this is few megahertz to hundreds of kilohertz. So this is the typical range of bandwidth. So we have two more such specification. One is called as slew rate, and other one is we'll discuss this slew rate, and the other one is input offset voltage. Input input offset voltage. We will just try to understand what is the slew rate and input offset voltage, and then come back to finding out what is the ideal value and typical value of slew rate and input offset voltage. So now let us try to understand what is this slew rate mean. So now it is slew rate. So slew rate uh, is nothing but rate of rate of change of output voltage. Rate of change of output voltage. How do we understand this is, suppose if you consider a waveform, an amplifier, let us consider a inverting amplifier, something like this. This is minus, this is plus. So let us assume that you have a gain of 10. This is 10k, this is 1k. Assume that you are applying a signal which is like a, so now this is R1, this is RF. So what is V naught is equal to, it is minus of RF by R1 into Vin. So here it is minus of 10 into Vin. If Vin, if this Vin is like something like this, assume that it is initially 0, it is initially 0 and then goes like 1 volt. This is like 0, now it is 1 volt. This is Vin. This is with respect to time. At time t is equal to t1, it is rising from 0 to 1 volt. So then what is the corresponding output voltage you're looking at? So output voltage is, this is V naught with respect to time. We are expecting this is, because 0, when the input is 0, even the gain is 10, it is 0. Then output is minus 10. So assume that this is minus 10 somewhere here, and it should reach somewhere here. So now instead of output voltage coming exactly 10 like this, so this is the ideal voltage what you're expecting. This is the ideal voltage what you're expecting. But actually what happens, due to slew rate effect, the output goes like this. Can you see your output is taking some time to go from 0 volt to minus 10 volt? Can you see it is taking some time? So this time there is, it's not coming down to minus 10 immediately, but it is taking some time. Can you see this taking some time? This is due to slew rate effect. This, instead of coming down here, it is coming bit late. So this is due to slew rate effect. Then how do I find the slew rate of this now? Suppose in that, if this is taking, or if the slew rate of this op-amp, if this slew rate is maybe 1 volt per microsecond. If the slew rate of this op-amp is 1 volt per microsecond, can I find what is this time? So what is slew rate is equal to, slew rate is nothing but del V naught by del T. That is given by, for this case, it is 1 volt per microsecond. So what is del V naught now? Del V naught is nothing but change in the output voltage. So output is changing from 0 to minus 10. The overall change is 10 volts. So this is 10 volt divided by delta T is equal to 1 volt per microsecond. Correct? So does this V volt will go with this volt. So then what is delta T? Delta T is equal to 10 microsecond. Meaning an op-amp having a slew rate of 1 volt per microsecond will take 10 microsecond to change from 0 to -10 volts. So this time is now 10 microsecond. Suppose that you have one more op-amp which has got zero point 0.5 volt per microsecond as the slew rate. Assume that this is the slew rate of the op-amp. This is slew rate of the op-amp. Then how much time does your output takes to again make a transition of this much? So can you see this delta T is now 10 volt, 10 volt, because this is what is. So let me just take it here. So what is this? So now slew rate is equal to 0.5 volt per microsecond. 0.5 volt per microsecond is equal to del V naught by del T. So this del V naught we are still considering it as 10 volt, and del T I'm supposed to find. Can I now find del of T is equal to 10 volt by 0.5 volt per microsecond? Then this will go with this. So that's what is 10 by 0.5 is 20. This microsecond goes up. Is it not 20 microsecond? So what is delta T? It is 20 microsecond. So now an op-amp having a slew rate of 0.5 volt per microsecond is taking more time for changing from here to here. So what should be the slew rate of an op-amp to have immediate transition from this 0 to -10 volt within no time? So this time should be 0. Suppose if delta T, if this delta T should be 0, then what is your slew rate? What is your slew rate? Slew rate is equal to del V naught by del T. Suppose if this becomes 0, this becomes 0, then what is slew rate? Slew rate has to be infinite. Slew rate has to be infinite so that output can change from one value to other value within no time. It should instantaneously change. So that's why slew rate ideally should be, what is the slew rate? It is infinite if it is not taking any time at all, which is the ideal case. So what is the slew rate ideal value? Ideal value is infinite volt per microsecond. This is the ideal value of slew rate. What is the typical value? Typical value changes from 0.5 to 10 volt per microsecond. This is always put in per microsecond. So this is not per second, this is per microsecond, because the switching will happen very fast. So that's why they are mentioned in terms of so many volt per microsecond. This is the slew rate of the op-amp. Suppose if you take one more example, suppose if you have a signal which is going from this to this like this. So if this is taking around 15 microsecond to change from -5 volt to +6 volts. What is slew rate? What is slew rate? Slew rate of the op-amp is, so can you see it is changing from 5 to 6? So then how much is the overall change? It is 11 volts. How much time it is taking? It is taking 15 microseconds. Then what is slew rate? Slew rate is, how much is 11 by 15? So it is actually 0.733 volt per microsecond. This is the slew rate. Suppose if it is something like this, if it is taking 15 microsecond to rise from -5 to +6, if it is this type of variation, then the slew rate of this particular op-amp having this transition is 0.733 volt per microsecond. So now we have understood what is slew rate. Slew rate is nothing but rate of change of output voltage. Ideally it is infinite volt per microsecond, but typically it is 0.5 to 10 volt per microsecond. 10 volt per microsecond. Then comes another parameter what we know that it is what is that? Mm, input offset voltage. So we'll just try to understand what is this input offset voltage. So we will again consider the op-amp. So we will consider uh, this op-amp here. So just to save pages, I'm just reusing this small portion of this page. Now this is the op-amp, minus, plus, this is so and so, this is V0. So what is V0 is equal to, we know that it is A0 times V plus minus of V minus. So this is V minus, this is V plus. Suppose if I ground both of them, so can you see V minus is 0, V plus is also 0, both are 0 0. So then what should be V0? V0 should be equal to A0 into 0 minus 0, so it is 0, so V0 is 0. This is the ideal case. But typically when I ground both the inputs, output may be some 10 microvolt. Instead of course this was supposed to be ideally 0 volt, but it is 10 microvolt. It's a very small, this is not 0, this is some non-zero value. This voltage, the output voltage when both the inputs are grounded, is known as output offset voltage. What is this 10 microvolt? This 10 microvolt is the output voltage when both the inputs are grounded, is called as output offset voltage. This is in terms of very small voltage, maybe 100 millivolt, 100 microvolt, 500 microvolt. This is in terms of microvolt or few millivolts. It may be 1 millivolt, it can be maybe 2 millivolt, or it can be 200 microvolt. This cannot be in terms of volts. So these are in terms of milli and microvolts. This is known as output offset voltage. So what is output offset voltage? It is the output voltage with both inputs grounded, with V minus is equal to V plus is equal to 0. These two are grounded. If you are still having some voltage at the output, it is output offset voltage. Now I should get output as 0. I should get output as 0. So now what I'll do, I will apply some input voltage either at non-inverting terminal or at inverting terminal, so that this output voltage, which is non-zero, will tend to become 0 volt, because I want to get this. I'm not getting it as 0 volt, but I'll apply some voltage so that I can make the output voltage as 0. What voltage you apply here to make the output offset voltage 0, output voltage as 0, is nothing but input offset voltage. Let me again clarify. So now you had this amplifier minus plus. If I ground this, assume that you are having some minus 10 microvolt, so this was supposed to be 0, but it is not 0. So what I'll do, I'll apply some voltage, I'll apply some plus minus or minus plus voltage, so that this minus 10 will become 0 volt. So what input voltage that you are applying here to make the output voltage 0 is known as input offset voltage. We have defined output offset voltage. What was output offset voltage? When you ground this, whatever that you are getting is output offset voltage. To get this 0, you are applying, to get the output voltage 0, you are applying some voltage at the input in order to make this 0. So that is called as input offset voltage, which will be ideally 0 volt. Meaning when this is 0, you are not supposed to apply anything. So that's why input offset voltage ideally is 0 volt. Typically it is few microvolt, maybe tens of microvolts, tens of microvolts. So we had this one more parameter which was not covered. Input offset voltage should be ideally 0 volt, but typically few microvolts, maybe 10 to 100 microvolt. Micro, you can see it is micro, very very small voltage. So we have covered 1, 2, 3, 4, 5, 6 parameters of the op-amp, which includes voltage gain, input impedance, output impedance, bandwidth, slew rate, and input offset voltage. Their ideal values, their typical values, and their units. You can see it is impedance means ohms, impedance ohms, bandwidth hertz, slew rate volt per microsecond. This is input offset voltage, it is volts, and gain don't have any unit. Don't have any unit. Is that fine? This is about the op-amp parameters. So then we have something what is called as feedback parameters. So in order to understand feedback parameters, let us consider an amplifier with gain A, B. So this is the amplifier. When I say amplifier, it is typically the voltage amplifier. This AV is voltage gain. This is V0. Let us say it as some V in dash. So naturally V0 by V in dash is equal to A, is equal to A. So what I'll do, I have an input voltage V in, it is applied here with plus symbol, and I am taking the output voltage and passing it through a feedback network, passing it through a feedback network, usually a resistive network with magnitude as beta, and applying it back to this with negative sign, and this is you're getting. So what is as per this, if I say it as V B, some feedback voltage, so can I write V in dash is equal to V in minus of VB. This is what, this is like a summer, this is like a summing parameter. So this plus of this, so in this plus, since it is entering with negative sign, that will become minus. So it's actually V in plus of minus VB is equal to V in minus VB. What is VB? VB is V0 into beta. So now let us, we are actually feeding a portion of the output voltage back to input. So what is VB now? VB is actually beta times V0. Beta times V0. Usually the beta is far less than 1. Far less than 1. Meaning if this is 2 volt, if you are applying only 10% of it, then it is 0.2. If it is 10 volt, if you are applying 5%, then it is only 0.5 volts. You are applying a fraction of the output voltage back to input along with the, so this input is this minus of this. So now we have two gains. One gain is this gain, the other gain is V0 by V in. You can see this is overall gain. This you can call it as, this overall gain includes the feedback. So this is called as AVF, that is voltage gain with feedback, or you can treat it as overall gain G. Overall gain G. So let us find an expression for the overall gain of this amplifier with negative feedback. So if we can write the expression for V0. So what is the expression for V0? V0 is nothing but AV times V in dash. V in dash. But this V in dash is nothing but V in minus VB. AV into V in minus VB. But what is this VB? This is V0 into beta. So I can write it as AV V in minus V0 into beta is V0. So I can write V0 is equal to AV V in minus V0 AV beta. I can put this entire AV V naught onto this side. Can you see now, is it not V naught plus of V naught AV beta is equal to AV V in? Now I can write V naught as a common factor. Is it not 1 plus AV beta is equal to AV V in? So can I write V naught by V in? So that's what V naught by V in, which is nothing but AVF, voltage gain with feedback, or overall gain. Can I write it as AV by 1 plus AV beta? This is the expression for the overall gain of this amplifier with feedback beta and with a gain of AV of the amplifier. Overall gain is given by AV by 1 plus AV beta. Looking at this, if you can see this AV, which was the open loop gain, AV is also called as open loop gain. AV is also called as open loop gain. This is, if you open this, I have only this much. Then I have loop gain. Then I have loop gain. Loop gain is this into this. So loop gain is AV into beta. So this is loop gain. So overall loop, you have an entire loop. If you start from here, come back to same point, you have this into this. So when you, this is what open loop gain of the amplitude. This is just when you're not feeding back, this is uh, gain with no feedback, with no feedback is AV. When you, what is this loop gain? Loop gain is when it is this. So now what is a closed loop gain? Closed loop gain is from here to here. That is output V naught by V in is the closed loop gain. Open loop gain is only AV, and this loop gain, you just loop is just only this. So I'm not considering this as the input voltage. Simply this gain, this into this is your loop gain. So we understood closed loop gain is nothing but AV by. So looking at this, since you have this denominator is always more than 1, can you see G will be certainly less than AV all the time? So this G will be always less than AV. That is, overall gain of the amplifier will be always less than open loop gain of the amplifier. Open loop gain of the amplifier. We can actually take some examples and then try to find out if AV is equal to some 300, if beta is equal to some 0.2, can we find what is AVF? So now what is AVF is equal to? It is AV by 1 plus AV beta. So can we find what is that? Is it not 300 divided by 1 plus 300 into 0.2? Can you see it is 4.91? Even though AV is 300, since you have a feedback factor of 0.2, the overall gain reduces to 4.91. So as I said here, overall gain is far less than AV. So overall gain is 4.91, the open loop gain is 300. So again take the same AV is equal to 300. Let us take beta is equal to 0.9. So let us find what is AVF. Is it not again AV by 1 plus AV beta? Is this not equal to again 300 divided by 1 plus 300 into 0.9? Can you see it is 1.107? The gain is almost closing to 1 now. Suppose you take one more case where it is again 300. If beta is 0.01, what is AVF? You have a very small feedback. You have a very small feedback. Can you see now it is 300 divided by 1 plus 300 into 0.01. Can you see it is now 75? You have a gain of 75. So now AV is 75 when beta is very small. So this is how you can able to find the overall gain AVF or G for a given feedback. So assume that you want to get a AVF of something like 12 from a AV of 350. Then what should be beta? What should be beta? So of course we can get the expression of beta in terms of AB and AF. So can we get it? So what is ABF is equal to, is it not AB into 1 plus A beta, AB beta? If you make the cross multiplication, is it not ABF plus AV into ABF into beta is equal to AB? So I can write beta as equal to AV by AB and ABF minus of ABF by AV into AVF. Will it now become beta is equal to 1 over AVF minus 1 over AV? So this is what, this will go with this will go with this, you'll end up with 1 over AVF minus 1 over AV. So now what is the example you have? You have 1 over 12 minus 1 over 350. So now what should be this? So it is 12 inverse minus of 350 inverse, it is this. So if beta is 0.0804, then out of 350, upon doing a negative feedback, you'll get so this is 0.0804. So this is, you have to have only 8.04% of the output should be fed back to input. So this is what the relationship between beta is equal to 1 over AVF minus 1 over AV. This is again derived from this. No need to remember this. If you know this equation, you can easily apply this. It is AVF by AVF minus 1 over AV. It is also possible. So assume that uh, if AVF is equal to some around 15, if beta is equal to 0.02, can we find what is AV required? So we can do this also. So how do we do this? So now we can get an expression for AV in terms of beta and AVF. So we have AVF is equal to AV by 1 plus AV beta. So can I write it as AVF plus AVF AV beta is equal to AV. So can I now write so let me take this AVF plus of what I have is, so AVF is equal to AV minus AVF AV beta is there. So can I now write AVF is equal to AV, I can take out common factor, is it not 1 minus AVF beta? So now what is AV is equal to, can I write AV is equal to AVF by 1 minus AVF beta? This is AV in terms of AVF. So this is AV value in terms of AVF. So I want to know what is AV if AVF is 15 and 15 into 0.02. So what is this now? It is 15 divided by 1 minus 15 into 0.02. So is it not AV is equal to, so 0.1, is this fine? So AVF is equal to this 15 divided by 1 minus 15 into 0.02. Suppose if it is 21 point, so or can I just do it like this? What you have is 15 alpha equals alpha A divided by alpha A, sorry, 1 plus alpha A into 0.02. Shift can. So let me see how much is the value that I'll get. I'll get as 21.42. So it is 21.42 divided by 1 plus 21.4242 into 0.02. Yes, so this AV will be equal to 21.42. If AV is equal to 21.42, I'll get uh, a gain of 15 with beta as 0.0. So this is AV is equal to 21.4. So this is the expression for, we have actually three expressions. AVF is equal to AV by 1 plus A beta. This is what is more interesting. Overall gain is open loop gain divided by 1 plus AV beta. If you want to find what is beta for a given value of AVF and AV, so this is the expression. If you want to find what is AV for a given value of AVF and beta, this expression AVF by 1 minus AVF beta. If you know this expression, you can derive these two. So these are the two expressions. Fine. So this is about the open loop gain of the amplifier, closed loop gain, and with negative feedback. Next, what we have is, so there is a possibility that you can have, this is we consider negative feedback. So there is a possibility that this can be positive feedback. This can be positive feedback. So this is an interesting parameter or interesting case where you have an amplifier. You have an amplifier with gain AV, and you have a feedback network with beta, and it is applied back to input voltage with positive feedback. And we know that if this is V in and V naught, so what is V naught by V in? When this is positive feedback, so we know that when it is negative feedback, it is this expression. It is this expression AV by 1 plus AV beta. If it is positive feedback, we will end up with AV by 1 minus AV beta. 1 minus AV beta is the expression for this overall gain with positive feedback. Assume that you don't give any input voltage. So if you don't give any input voltage, if you make this AV beta, which is nothing but the loop gain, if this is equal to 1, do I have a condition where it is 1 minus 1 is equal to 0 and you may get it as infinity as the overall gain? So this is the condition for getting oscillations. Meaning interesting circuit in electronics where you don't give any input voltage. So here this is a circuit. This is a circuit where you are giving nothing. You are giving zero input, but you get some output voltage. This is called as oscillator. When do you get this oscillation without the input voltage? This is possible only if the circuit, if this circuit has a positive feedback and A beta is equal to 1. When I say A beta, AV beta is equal to 1. Positive feedback should be there. Along with that, this A beta should be equal to 1. Then only without any input voltage you can get the oscillation. This condition of getting oscillation without input is called as Barkhausen criteria. So this is here Barkhausen, Barkhausen criteria. So a electronic circuit with positive feedback with loop gain is equal to 1 is the condition to get the oscillation. That's why it is being named after Barkhausen, who has found this is called as Barkhausen criteria. This is Barkhausen criteria. Example of this type of circuit where you are having a positive feedback and A beta is equal to 1 is this Wien-Bridge oscillator. Wien-Bridge oscillator. So now this is realized using Opamp. This is minus plus. You are using this negative feedback to get a desired gain from this op-amp, which is RF and R1. Now you can see you are providing a positive feedback also, that is using this network of resistor and capacitor in this way. So I have one R, one C, another R, another C connected this way, and this is given back to this here. Can you see this is fed back here? This is output voltage fed back to input to the non-inverting terminal. Can you see this is positive feedback? Can you see I'm not giving any input voltage? Input is grounded. So here we had positive feedback. Positive feedback is this. Can you see some output is fed back to this? You may argue that, sir, we are providing this also. Yes, you are providing this to have a desired gain using op-amp, but there is no input given. There is no input given. So now we have this feedback factor using this RC network, this fashion, this fashion. This will result in some beta value which will be equal to 1 by 3 at a particular frequency. You call it as F naught. So there is a particular frequency of oscillation. Only at that frequency of oscillation F naught, this beta is 1 over 3. How do we make this AV beta is equal to 1? So AV beta is what? 1 over 3 should become 1. So when does this equation is satisfied? This is satisfied when AV is equal to 3. What is this AV? Suppose if the signal is feeding back here, is it not looking like a non-inverting amplifier? When RF 1 over RF, sorry, 1 plus RF by R1 will be your AV now. This should be equal to 3. When this gain of this amplifier becomes 3, when this is possible to become 3? So when this is 1 plus 2k by 1k is equal to 3. Is it not 3 now? So when this RF is equal to 2 times of R1, I will have the condition of A beta is equal to 1. Then I'll get the oscillations at a frequency of F naught, which is given by 1 over 2 pi RC. 1 over 2 pi RC. Meaning, if you have an amplifier, so let us consider that this is 1 kilo ohm. This is 0.1 microfarad. This is again 1 kilo ohm. This is 0.1 microfarad. So now what is F naught is equal to? It is 1 over 2 pi 1 kilo ohm into 0.1 microfarad. If you find out that value, can you see it is not 2 into uh, pi into 1 exponential of 3 into 0.1 exponential minus 6. Can you see how much is that? Is it not 1.59 kilohertz? This is the frequency. At this frequency, this beta is 1 by 3. So make this equal to 3. So can I make it as 1 kilo ohm and 2 kilo ohm? When I make this 1k, this is 2k. Is the gain 3? Is this beta 1 by 3? Now you'll get the oscillations at a frequency of 1.59 kilohertz. Where is the input given? You have not given any input at all. So without giving input, you can get the oscillation at a particular frequency F naught decided by this network, provided A beta is equal to 1. What is A? It is now 3 because beta is 1 by 3. So when this is satisfied, you will get oscillations which is called as Barkhausen criteria. Barkhausen criteria. So we have one more such oscillator where we can able to get the oscillations. It is again using the op-amp. This is what you have: minus, plus. You will have a negative feedback again applied. This actually means negative feedback because you are applying to inverting terminal. This is RF, R1. This is now grounded. Now in the previous case, you can see we actually provided a negative feedback. Now you are providing, sorry, this is negative feedback, but can you see this is positive feedback? Whatever that is required to get the oscillations in the form of you need to have a positive feedback. That's why we provided a positive feedback. Now you can see, so intention is to make A beta is equal to 1. A beta is equal to 1. So you have, this is what you have AB by 1 minus A beta. So when this becomes 1, then you're going to have, this is infinite, so V naught by V in. Even with V in as 0, you can get some output voltage. So that's the condition. Now let us see what happens here. We have a negative feedback. So when you have an inverting amplifier, is it not minus RF by R1 is your AV? This is AV. So what we'll do, now we just give this feedback. Now feedback is given through this RC network. Can you see I have one RC network, I have another RC network, I have another RC network. There are three RC networks used to feedback the signal. RC, RC, RC. Now we are not providing negative feedback. Sorry, we are not giving positive feedback at all. Can you see, is the signal going back here? So there is no positive feedback. You have negative feedback. When it is negative feedback, do you have it as 1 plus AV beta? Because you are providing negative feedback. When it is negative feedback, the expression is AV by 1 plus AV beta. Now, does the oscillations occur here? Yes, oscillations still occur even though you are providing negative feedback. Now the question is, I have to make this AV beta as minus 1. If I can make it minus 1 even with this negative feedback, is it not, now you have 1 plus of minus 1. So what is this? It is infinity. See, now I'm only giving negative feedback, but still I can able to make 1 plus, in this 1 plus A beta, if I can make this minus 1, then it is possible to get oscillation. Now, is this, suppose if you're applying some input voltage here, is this the gain? So what is AV now? AV is equal to minus RF by R1. Suppose if this is the feedback network, you can see this is what is feedback network. In this feedback network, in this oscillator, this beta is equal to 1 over 29 at a particular frequency F naught. At a particular frequency F naught, this beta is 1 over 29. This beta was 1 over 3 at a particular frequency. So this beta is 1 over 29 at a particular frequency. So when beta is 1 over 29, to make AV into beta is minus 1, this is equal to what? So this is AV and beta is how much? 1 over 29. So then what should be AV? If AV is equal to minus 29, so then you'll get the oscillation. How to make this AV as minus 29? Make this as 29 times of R1, then you'll get it. So what is AV here? AV is minus RF by R1. If I make it as minus of 29 R1 by R1, does this go off? So do you have it as minus 29? Do you have AV as 1 over 29? Sorry, beta as 1 over 29. Then what is AV into beta? So does AV into is beta, does it becoming 1? So when it becomes 1, does this become 1 plus of minus 1? Is it not becoming 0 in the denominator? So will it not become infinite? So even by providing negative feedbacks only, but by achieving this A beta is equal to minus 1, I can still achieve oscillations using this type of circuit. This is called as RC phase shift oscillator, because you are using 1, 2, 3 RC networks. So this is RC phase shift oscillator. So now let us find an example for this. Okay, let us find out at what frequency this oscillates. This oscillates at a frequency F naught is equal to root 6 by 2f RC. So this is the frequency at which this will oscillate, root 6 by 2 pi RC. So let us find an example here. So let me just take it as 1K, 0.1 micro. Again this is 1K, 0.1 micro. This is again 1K, 0.1 micro. here this is my R1, this is RC, 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 this is R1 going to inverting terminal, the non-inverting terminal is grounded. I'll apply like this. I will use it as 1K. Now I will use 29K. This is RF. Can you see now I'm just feeding it back here. This is feedback signal, and this is grounded, grounded, grounded. Now I'll get oscillation of frequency F0, where F0 is root 6 by 2 pi RC. What is 2 pi RC now? So it is root 6 divided by 2 into pi into 1 exponential of 3 into point into 0.1 exponential of minus 3. It is, sorry, minus 6. Can you see it is at a frequency of 3.89 kilohertz. I'll get the oscillations provided this gain is minus 29. AB is, so what you have is ABF is equal to AB by 1 plus AB beta, but AB is minus 29, beta is 1 over 29, so this entire product is minus 1, so this is 1, so your denominator has become 0, so this is now oscillating. So the difference between this is you are providing a positive feedback, A beta is equal to 1. Here you are providing a negative feedback, A beta is equal to minus 1. So this is what AB beta is equal to minus 1. Even though you are providing a negative feedback, because this AB beta is minus 1, this denominator will become 0. So this is what RC phase shift oscillator. This is Wien bridge oscillator. So both should satisfy. A beta is equal to 1 for a positive feedback, should be minus 1 for a negative feedback. So typically what should happen is A beta should be 1. A beta should be equal to 1 is the Barkhausen criteria, provided you are giving a positive feedback. Okay, that's it about the oscillators and op-amp parameters on the feedback network. Thank you.